In contrast to last week's lectures that were probably a little bit on the more relaxed side, those slides are going to be a little bit on the more technical side, at least. So there'll be equations. So basically what I'm going to talk about for as long as the time it takes for Deepak to show up is a little bit about hierarchy and structure in modeling, well, basically data. And because this is actually, I think, a really important issue. So first I should probably say thanks to some of the people involved, and I've tried to pick the most favorable photos of them, right? So let's actually start with something very gentle. So there shall be slides eventually, equations eventually. But let's start with something very simple. So the simple thing that we're going to start out with is clustering, right? And so what I can do is I can cluster dogs and cute cats and dinosaurs, right? And if I were to do that, then something called the Dirichlet process, which is basically a model of having variable numbers of clusters and essentially inferring the number of clusters at the same time as you infer, well, the cluster IDs themselves, is a pretty good strategy. So without going into all the math that goes with it, because that would take more than just 5 minutes, you can think of the mechanistic interpretation of this, which is sometimes also when people talk about the Chinese restaurant process in this context. Who has heard about the Chinese restaurant process before yet? Oh wow, that's pretty good. Okay, so if you haven't heard about it yet, here's how it goes. Imagine a Chinese restaurant with an infinite number of tables. Okay, so similar to Hilbert's Hotel, Chinese restaurants. Okay, first customer walks into the restaurant. Okay, well, he sits down at the table and, well, eats something. And then next customer walks in and he sees where people are sitting. In this case, there's just one customer there, right? And now, with probability proportional to the number of people that sit at this table, he joins the table, because people are social animals. And with a constant fraction, with a suitably normalized constant, he picks a new table. Let's say this constant equals 2. Then, well, if there's only one person sitting at one table, then he picks with probability 1 over 1 plus 2, so 1/3, the table that's already got one person sitting there. And with probability 2/3, he picks a new table. Now the third customer comes in, and with probability now 2 over 1 plus 1 plus 2, right? He picks, with probability 1/2, he picks a new table, and with probabilities 1/4 each, he picks one of the two existing tables. Okay, so what you can see is that this very clearly gives you a distribution over partitionings of, in this case, well, customers to tables. And I forgot to mention to say that while the restaurant has an infinite number of tables, and the tables can hold an infinite number of people, there's only space for one dish per table. Yeah, okay. It's a mathematical construct. So what you basically get is, through that, is a clustering. So you could imagine a new image comes along, and, well, if it fits the dinosaurs really well, okay, it goes to the dinosaur table or the dog table or the cat table. And if it doesn't really, it generates a new table. Okay, this is the Dirichlet process without math. Now, you could argue that, well, maybe cats and dogs are more similar than cats and dinosaurs. And, well, we can make this a little bit more extreme to really drive home this point. If I have cats and dogs, and then I have more specifically German Shepherds, and here are some poodles, and there are cats, and you could argue that these are really close, right? But, okay, and then there are cameras, then it probably doesn't make sense to have a flat clustering, right? And that's exactly what Adams, Garamani, and Jordan did, right? So they said, well, maybe we can cluster cats and dogs, but then maybe dinosaurs are one level higher up, and cameras are a different beast yet again. And yeah, basically, well, the two different types of dogs are really something that belongs to the dog cluster. Now, this is a hierarchical modeling where you basically have a hierarchical structure that is imposed upon, the sets of objects that you have in your collection. The reason why I'm going through this in a bit of detail is because people typically confuse, and this is me included, various notions of hierarchical modeling. So you can have hierarchy in your data structure. You can also have hierarchy in the sense that, well, first one thing affects the data, then the other thing affects the data, and you have hierarchy this way. You can have a lot of other more sophisticated structures in your data. The point is, you need to actually specify what you mean by hierarchy before you can say, well, I'm doing hierarchical modeling. Okay, this is one, and the paper by Adams, Garamani, and Jordan, which is a really nice paper, they applied this to images. They made some strange decision about, the hierarchical inheritance between clusters, but basically what they got out as the top-level cluster when clustering all the images. Can somebody guess what that would be? I mean, you would think this is like the God image, right? Okay. Anybody guesses? Well, if you've read the paper, this is not okay. That doesn't count. Somebody who hasn't read the paper. Come on, it's Monday morning. Yeah. A cat? Not quite. It's an inanimate object. Okay, hint. A lawnmower. Yeah, exactly. That actually suggests more that the generative process that, they made certain design choices to keep the variance at bay, and I think if they changed it a little bit, they could have probably gotten a more meaningful top-level image. There's another thing, and we already talked about that last week, namely factorial representations. So this is latent Dirichlet allocation, and there you don't assume that each object just belongs to one category, but it's composed of a sparse mixture, preferably sparse, of a couple of components. So think of the traffic light. The traffic light's either red, green, or yellow, and that's about it. Whereas the pixel on your computer screen is a mixture between red, green, and blue. So in both cases, we have three colors to describe the state. However, in one case, we have a mixture between the states. In the other case, we have only one of the three. And that gives very different color representations. Unless I was to switch the traffic light so quickly that your eye would blur everything. But yeah, we're not worrying about that here. This, by the way, is an idea that people used to use a very, very long time ago when basically high-resolution displays were really expensive. So they would actually have a red, a green, and a blue light flashing at alternating orders very rapidly to fake an RGB display. And these displays were really awful to look at. But so it's not totally unconceivable that you could do this. So the next thing that you can do is you can have what's called a hierarchical Dirichlet process. And then there's also something called a nested Chinese restaurant process. And as you can already see, the nomenclature for those models is confusing at best. So the hierarchical Dirichlet process is one where you basically have a distribution. And then at the next level down in your model that you're trying to describe, you assume that the distribution of the child is related to the distribution of the parent. So here's an example of what you could do. You could have that, H, so this is again our Dirichlet process that we saw before. This would be, the model that describes, language. And let's just do something as primitive as bag of words. Now, if I have such a primitive model as bag of words, then G0 is going to be, for instance, the base level language distribution for all English documents. And then what I can do is I can use GI to model regional dialects. And so what you would assume is that G0 encompasses the entire vocabulary that's also, prevalent regionally, because this is the whole English language. And you would then assume that GI is drawn by using G0 as a prior, but it could obviously be that certain words occur much more frequently here than somewhere else. So for instance, I would imagine that in the Pittsburgh language model, the words pirates and stealers are much more frequent than, let's say, in the Bay Area. Okay, so this is one way of having hierarchy by essentially inheritance from the parent to the child. So basically what you simply do is you have one reference distribution. Here's just some distribution over tokens, which gives me the base language model. And then I use this base language model as a prior for the GIs. Okay. So you can do that. What you can also do is you can play the same game for topics. This gives you something like the nested Chinese restaurant process. So where basically you apply this now not to the language model itself, but just to the topic distribution. One of the problems with this is quite often you need to actually predefine how these graphs are structured, because otherwise it just gets a little bit messy. Okay. So let me just write out exactly what happens in the nested Chinese restaurant process. So for each node in this possibly infinite tree, you go and draw a topic independently. And if for each document, you go and draw a path over the tree, and then basically use this as a way of getting the word distribution and so on. So in other words, we have our topics here. And then if we have a document there, it actually generates its words by going down the tree. Which is kind of nice, and it actually fits documents a lot better than a flat topic model. Because what you can now do is you can have things like, photography as one level up, and then further down in the bottom you can have all the various differentiations about photography, which is neat. Okay. The problem with this approach is that quite often, you have actually variable degrees of resolution in interests, in content, and so on. So if you think about what you're really interested in, there's a whole bunch of things that you're very, very, very specifically interested in. So maybe within, computer science, you're interested in machine learning. At least I hope so, otherwise you wouldn't be here. And then within machine learning, you're interested, for instance, in non-parametric Bayes. And then, by the way, within non-parametric Bayes, you particularly like the Indian buffet process, right? This is a very, very specific narrowing down of interests. But maybe, besides being very specifically interested in the Indian buffet process, maybe you also kind of have a passing interest in kernel methods. And besides that, maybe you like classical music, and then you like a very specific painter. And then maybe you speak English, right? So what I've just described is different levels of detail of interest and different types of interest. And if you think about yourself, you may have different degrees of depth and breadth for different interest types. And the models that I described so far don't capture this. So there are some models which are pretty good at essentially just covering, the breadth. And there are some models that are pretty good at covering the depth, but none of them actually captures both. And I'm kind of sort of already leading you towards what you would want to do if you want to capture depth and breadth at the same time. And I'll show you, how the math works on the next slide. This doesn't only happen with users. You might also have that with documents. You might have an article about some very specific event, like, for instance, yesterday's Soccer World Cup, right? So then you have, very specific details about very specific soccer players. And then you have, by the way, the World Cup, and then maybe it's about Brazil, and then maybe you have a couple of words about, how life in Germany and Argentina is, respectively, right? And then maybe because it's on the CNN website, you have 3 lines underneath, plugging some other program. So that would be a typical article. So what we therefore want is we basically want to have a tree distribution per object. And this tree, with various levels of depth and breadth, will then cover the content. So what I'm basically going to do is I'm going to attach weights to the possible internal nodes of the tree, and that set of weights should represent what's going on. So let's have a look at this in a bit more detail. So basically what I do is I take a generative process that models a global interest distribution of what people are interested in. So let's say here is Schweinsteiger, here's Messi, here is, well, Klose and whatever, and then maybe, here's the Cristo Redentor, and, well, it just goes on like so, right? So, and this is, one gigantic object. So this is in all details, all the things that people might want. Now, for each document and for each word, what you do is you basically select a path within a document. So this is a proper subtree of this tree, ditto this one here. And then if within that path in the document, if I decide to add a new topic, so this is the same thing as opening a new table in the Chinese restaurant process that we saw before. Then you go and see, well, do we already have such a topic in the global, language model? Okay, if it's there, it's good. If not, then I also add a new edge in the global model and then add a new path. So basically, what happens is I always make sure that the global tree is a proper superset of the local trees. Well, let's have a look at an example. So let's say I sample this path. Well, this path, can somebody find it in the tree? In the global tree? Well, I guess that's really easy, right? That's fine. So there was that one there. Now, if I decide to, add a new edge in the local document, okay, well, be it so. Remember, we had this. So now that local tree grows, but it's still a proper subtree of the global tree. So no big deal. However, if I go and add a new, topic that's locally new and also globally new, then I also need to augment the global tree. So all you have to do now is, at the global tree, is keep track of the counts of essentially how many times this global tree was invoked. This is a little bit more tricky than just keeping track of the aggregate counts, because you need to basically attribute blame as to where those things came from. But there's a couple of really nice, essentially tree samplers which do this. But this is the conceptual structure of having hierarchy, variable depth, and variable breadth. So let's actually see how this behaves in practice. So this is a paper we had 2 years ago. So basically, for each word in a document, you go and sample the node. Then if it's globally new, you add a new node, and otherwise. So basically, all we did is, for the emissions model, we just used a multinomial. Okay, so here's what you get for the NIPS corpus, for instance. And it's kind of cute because, you can see, so overall, you get just the fact that it's a NIPS paper, right? Model, systems, control, policy-based paper, approach, results, data. Any self-respecting NIPS paper has to have that. At least this was 10 years ago. I mean, by now, probably deep would be also a word up here, right? And then, remember, these were the times when kernel methods were actually quite popular. Distribution parameters, Bayesian vectors, data, and then it would, this is actually going towards non-parametric. So then you have the algorithm inference sampling and approximate iterative, and then you have the more stochastic process papers. Can somebody get Deepak, please? He doesn't find the entrance. Okay, so, and then for reinforcement learning, you had the multi-agent, and then you had the, more state distribution types of papers. So what you basically got is, you can now clearly see that, you have various levels of detail, and you also have various levels of resolution. The entire thing also fits the data really well, and here you can see. So I'll just continue talking until Deepak is done setting up, but let me just introduce Deepak. He's director of all things machine learning and recommendation at LinkedIn, and I think probably the driving force behind essentially all adaptive estimation at LinkedIn. So it's a great pleasure to have Deepak Agarwal here. Let's give him a big applause. And for location modeling, you simply have to read the paper. Okay. So I'll plug you in, don't worry.